All right, continuing on our 5.2 lesson. On our last lesson, we covered mean, median, and mode, and then just barely introduced our misleading graphs. We're going to continue on from there, just discussing our misleading graphs. Now, there are a number of ways that graphs can be distorted, either on purpose or on accident. Now, what kind of graphs might we distort? Now, graphs are just kind of visual ways to show data. So we can use bar graphs, line graphs, pie charts, something along those lines. Now, even though we think that those are just displaying the data, so you can't really tamper with them, you actually can. And here are some ways that you can do it. They can be distorted by starting either the vertical or horizontal scale at some point other than 0. Normally, if we go from here and up, we would start here at 0 all the way to 10. That way, if we have one bar that goes up to here and one bar that goes up to here, it looks like this bar is twice as tall as this one because, well, it probably is twice as tall. If this one came up to a 2, this one came up to a 4, well, yeah, that would look like those ones are, one is twice as tall as the other one. Let's say, however, that this didn't start at 0. Let's, whoops, the whole thing. Let's say it started at 4 and went to 10. Now, if it was 4 and 10, then this one might just be a 5, and this one might just be a 6. So even though this looks like it might be twice as tall as this one, 6 is not twice as big as 5. So we started at a different point other than 0, which makes this look a lot taller than this one when it shouldn't be. It should really only be just one bigger, not twice as big. So starting at a point other than 0 is a good way to kind of fool people or distort the data to make it look one way or another. If we use intervals of scales that are not evenly spaced, so same kind of idea. If we have a big number line here and we space them something like this. Now let's say we had 0 and 10, or what we'd think would be 0 and 10. So with all of these tick marks, we think it would go 0, 2, 4, 6, 8, and then 10. Well, maybe this one wants to go 0 to 2 to 3 to 4 to 8. And then all the other numbers are somewhere in between. Even though these look like they're all evenly spaced, the numbers would tell us that they're not. So if we're halfway in between here, that should be a 9. Halfway in between here should be a 1. But halfway in between here would be like a 2.5. So this one, the spacing has 2 numbers in between, while this one only has 1. So we have to be careful at what kind of intervals or what kind of spacing our lines are giving us. So it's very important to read what the graphs are getting at or what they're saying. Now they can also be distorted by using inappropriate area or volume models. So if they're trying to show you something using a picture, the picture might be a little bit off from what it's actually trying to describe. They can also be distorted using percentages when actual quantities would be more appropriate, or vice versa. So maybe they're trying to show you the percentage of something, and the percentages are really, really close, but they want to use actual numbers and say, oh, this one is only 4 and this one is 20, when really the 4 is still 50% and 20 is still 50% of their respective total amounts. So again, we want to make sure that we're comparing things evenly, essentially is what we're trying to get at. So here are some examples of what that might look like or how that might be. Using this graph or this chart on the side, we're comparing 2 different batteries. The Extra Life batteries have 200 plus hours of battery time, and the regular brand X batteries have 100 plus hours. Now let's think about how those actually compare. 200 hours and 100 hours means that this one should be twice the amount. Now, how do the number of hours of use claimed for the extra batteries compare for the brand X battery? Well, the Extra Life would be 2 times as much. We're just going to say 2 times as much. It's doubled in a sense. 200 is double of 100. Let's take a look at this picture here, though, or this battery. If you look at it, if we were to take, I'm going to take this red outline, this fits our battery exactly right there. But if we try to put it over here, whereas on this battery, only one of them would cover the whole thing, over here, we need 4 of them to cover the whole face. So going from an area perspective, this front area, looking just at this one, even though it's twice as tall, it's actually 4 times the amount of area over here. So that isn't necessarily an even comparison. Let's look at the depth though. If we use this blue one to look at the depth, put the blue one on the side here. Again, we'll have another blue one. Matches up perfectly with this side. And we're going to match it up over here as well. There are again going to be 4 on the side of it. So on the very front, there are 4 times as many, which means on the side there are also 4 times as many. So let's think about this in a 3D way. How many of these batteries would fit onto this battery in total? Well, we can almost kind of see it if we complete the lines here. I'm going to cut this across like this and cut this across like this. There would be 4 of these batteries on top and 4 of them down here. So there are actually 8 batteries of this size put into this big battery here. So how would the volumes of these 2 bars representing the batteries compare? Well, it's actually 8 times as big. So even though our height, yes, this height is 2 times the height of this one, because 200 hours and 100 hours, but when we draw it out 3-dimensionally like this, making the height be twice as big makes the volume 8 times as big. So why does the graph give misleading impressions of the comparison lifespan of the 2 brands of batteries? Well, this one, it's true, it's a lot less than this one. It's half as much. Or we could say this one is 2 times as much battery power as this one. But according to the graphs, it looks like it would be 8 times as big, or it looks like it would be 8 times as long, when really it isn't. So this graph, or this representation, is actually pretty misleading. Let's look at these examples below. We're going to look at 2 bar graphs. Now, they both give us the same exact data. We're looking at the female workers in millions of the workforce during a certain year. So, during 1960, according to this one, it looks like there were a little over 2 million women working. Same thing over here, 1960, a little bit over 2 million women working. Let's jump ahead to 1980. It looks like there are a little over 4 million women working. 1980. Same exact data, a little over 4 million women working. Now the difference here is the one on the left starts at a 0. The one on the right starts at 1. Now all of these are cut off the same amount, so the jump from here to here is the same as the jump from here to here, but because this one starts at 1 and this one starts at 0, our graphs look a little bit different. So in the graph at the left, which bar is twice as long as the bar for 1960? If we start with 1960, remember that was a little bit above 2 million. We'd want one a little bit over 4 million, so it looks like 1980 is about twice as big as that one. So 1980 is the bar that's twice as much as 1960. However, looking over at our right one, which bar looks to be about twice as tall? So if this one is 1960, we want about twice that amount. So that'd be around here, Well, it looks like 1970 would be twice as tall. So again, just looking at the visual, it doesn't necessarily match up with the data. In which year was the number of women employed about twice as great as the number actually employed in 1960? Again, the real numbers would suggest that it should be 1980. So which of these graphs makes a better representation? It looks like it would be the 1980, or the left one over here gives us a better graph. Which graph gives a more accurate representation of that data? Again, we would say the left one looks to be much more accurate. Why is the other graph misleading? Why does this one not necessarily represent what we're trying to get it to say? Well, it looks like the data is increasing faster sooner. So even though I'm going from 1960 to 1970, in the real situation, it didn't actually double, but it looks like it did double in this one. So it's actually kind of, I don't know, misleading you, almost lying to you in a way. Explain why proponents of government funding of daycare centers might choose the graph on the right to support their position for increased funding. Well, again, they might want to make it look like more women are in the workforce at an earlier year. So if they can show that, look, by 1970, there were twice as many women in the workforce, then they could say, well, that's why we need more government funding. So they might be able to use this data to help them or skew it towards their position, even though it's not as accurate as it probably should be. How can we use technology to create these misleading graphs? For an example, a school gives the MCA test and receives less than favorable results. They choose to represent their scores in a way that makes them look better than they actually are. In their district, only 40% of the student body met the standards and 60% did not meet standards. So, using Microsoft Excel, we can create a pie chart and rotate that image to make it look better in our favor. So, all we'd have to do if we were in Microsoft Excel is set up our data, passing only 40%, failing 60%. We would go to the top and insert a pie chart, and we'd make it three-dimensional. So you just have to click on the options and make it a 3D rotational. Step 3, we would rotate it to our preferred content. So we would make it so that here you can kind of see normally it looks like it's pretty obvious that more people were failing than were passing. However, we can rotate our preferred content and our preferred view so that we're kind of looking at it from the side and not so much from on top, and we turn it so that this pass piece comes out in front of us. Now, even though the center of the circle is up here, here's the center, and it kind of opens up like this, kind of looks like a Pac-Man, it still does that. It still opens up kind of like a Pac-Man. It's just harder to see because it's 3D, and it's kind of popping out at us. So in a sense, this chart is almost lying to us. It's misleading in a way. It makes it look like more people passed than actually did. This one looks like a ton more people passed than failed, even though it's the exact same graph as this one. It uses the same exact data. So this should all show you how or why we can use data, especially in graphs, that might be misleading.